Today, I've got a conversation that I had with physicist Hans Schantz. Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. I had a very interesting conversation with Dr. Hans Schantz, a remarkable polymath, a theoretical physicist turned engineer, inventor, entrepreneur, and science fiction author. Driven by a desire to understand how the world works, he studied physics, ultimately getting a PhD in theoretical physics from UT Austin, where he studied under Dr. John Wheeler. This did not satisfy Dr. Schantz's curiosity, though, because it was in the style of the Copenhagen interpretation of quantum mechanics, which emphasizes calculation of the few things amenable to calculation over understanding what's actually going on. When he couldn't find the answers he sought in the ivory tower, in the grand tradition of discovery, he started investigating the thing for himself, studying applied electromagnetics, and joined an engineering startup, invented novel antenna systems, figured out a way to localize transmitter tags using the near-field properties of low-frequency, long-wavelength signals, and co-founded his own startup to commercialize the technology. In the process, he earned over 40 patents. With Dr. Schantz's hands now dirty with practical knowledge, he developed new models and insights about electromagnetics. But if you know anything about academia, you'll know the next part of the story. Dr. Schantz's ideas did not catch the attention of the establishment, so while he's given talks at various universities and even published a paper in a prestigious journal, he hasn't gotten traction. It has been said that science progresses one funeral at a time, with great justification if you read the history of science and how long it sometimes took for convincing evidence to overturn long-held theories. And while Dr. Schantz waits for more than a few funerals, he's decided to use his gift for writing to spread these ideas to people who share his interest in how the world works. Thus he's writing a 3-volume set of books called Fields and Energy, the first volume of which is coming out shortly. Intrigued, I invited him to come talk about it, and he graciously agreed. The result was a nearly 2-hour-long conversation, which I found riveting. Well, the parts where Dr. Schantz was talking, anyway. And I hope you will too. So, I remember a question I had asked you a long time ago that really, in your answer, really intrigued me. And I was asking about when we do radio waves, whether is it truly the case that the frequency that you're using from the antenna is actually the frequency of the emitted photons, or is it there's like a physical property of the antenna that emits photons and we're just modulating a carrier wave? Kind of like when you use an LED in fiber optics, you're just modulating a wildly higher frequency photon emitting source. And you said one of the problems that we have is that the things involved are just way too the energy is so low you can't detect an individual radio wave photon. So there's some problems with trying to find the answer. There's theoretical answers, but to actually answer it in a practical sense of just observing one of them and measuring the energy is just impossible because they're in some sense too small relative to the world we live in. And it struck me as very interesting how little we know about things that we use every day and are so fundamental. Which isn't to say that there are no answers by any means, but just that it's so interesting that there are these questions, and a lot of people I've noticed sort of they're not even very interested in asking those more fundamental questions that, things regarding to circuits and radio waves. When I've talked to a lot of people, I'm given these very abstract models to just use and sort of told, here's the model. It's you're doing this thing with these complex numbers. So it's just that.
Yeah.
Clearly, electrons aren't complex numbers. So, it's a reason I'm very interested in your upcoming series of books, getting into what actually is this stuff. Mm-hmm. So from there, could you just give an overview of it? Because I know it's a trilogy of books.
Oh, sure. Well, the conventional wisdom, to the extent physicists don't just say, shut up and calculate, here are the equations and take them and run. To the extent that conventional physics has a model or a picture of electromagnetism and how it works, they assume that it is one thing, a photon, which somehow simultaneously combines the mutually contradictory properties of being a non-local distributed wave and a localized particle. And that view leads to paradox and confusion. In my thinking, electromagnetism is due to two things: to waves, which behave, fields which behave like waves and are distributed and non-local, and energy, which in the quantum limit looks like a stream of particles. So, I mean, the short answer is conventional physics thinks electromagnetism is one thing. I think it's two. I think it is fields guiding the flow of energy. And in example after example, I can show how if you try to track how the fields move in a physical system, they're doing one thing and the energy is doing another thing on a completely different space-time trajectory. So they really do have to be two separate things. And my thinking follows from a lot of ideas on electromagnetism, which were pioneered in the late 19th century, but kind of got lost and forgotten and swept under the rug with the development of relativity and the development of quantum theory and the abolition of the ether and the insistence that there could not possibly be a physical mechanism operating in free space, which gives rise to electromagnetism. And those misconceptions have really hindered our understanding of physics. Now, back in the 1880s, Oliver Lodge kind of famously said or asked the question, "What is electricity?" and acknowledged, "We don't know." And even today, if you ask what is electricity, well, we've learned some more about it, but fundamentally, we still don't know exactly what's going on. We just have a few more clues, a few more pieces of the puzzle to try to figure it out. And that's what I've been working on and what I'm going to be sharing in my books.
That's fascinating. Now, let me ask you a question about the ether. Because the ether, of course, it's a popular whipping boy in science textbooks, because you always need to make fun of the people who came before you in order to establish how much better you are. There may be some other reasons too. That's my impression as to why you always have to have that kind of thing. Those dolts, they believed in the four humors, they believed in the ether, etc. Right. But how different is the ether from space-time? Because it's commonly accepted now that space is actually a substance that warps, and waves of warping space move around and so on. So is that actually meaningfully different from, obviously it's verbally different, but is it meaningfully different than the ether idea?
That is a very, very good question, because it segues into a somewhat long but interesting story. Because the reason we mock and make fun of the ether is because fundamentally of a guy named Ernst Mach. He's more famous because Mach numbers, the measurement of the speed of sound, were named after him. But he also was a very influential historian and philosopher of science. He wrote a great book, History of Mechanics, for instance. And in philosophy, he came up with a school of thought, or popularized a school of thought, that through other people's contributions evolved into a perspective called positivism. And what Mach believed was that physicists should focus on observations. We should look at what we can see, what we can perceive, and not engage in idle metaphysical speculations about what might really be going on behind the scenes. Just look at the data, look at the numbers, focus on that, find the connections between them, and that's what physics is supposed to do. Well, there was a young Swiss patent clerk who was extremely impressed with Mach's thinking, and when he would get together with a bunch of his friends and read the great thinkers of the day, one of those thinkers was Ernst Mach, and Mach made a great impression on this young patent clerk. Now, another person this patent clerk read was Poincaré, and Poincaré had this marvelous theory that taking a look at the results of the Michelson-Morley experiment and work that had been done by people like Lorentz on the concept that You have phenomena like time retardation and length contraction in moving electrodynamic objects. This patent clerk, who, not to spoil the story, his name is Albert Einstein, he came up with a way of taking all of the work that Poincaré and Lorentz and Fitzgerald and all the people who'd been working to understand the electrodynamics of moving objects. And Einstein realized that we could express it in terms of what the observer sees. And what the observer sees is the speed of light being constant in all inertial reference frames, and the laws of physics appearing the same in all inertial reference frames. So Einstein took those two principles, and from those principles was able to show that all of the other ideas of relativity and the Lorentz transformations and so forth, they all followed from those two principles. No ether needed, no mechanism required to explain it, just logical deductions from two fundamental principles. And that really impressed a lot of people. Not initially. I mean, Einstein gained traction in Germany. Planck, in fact, some people have argued that Planck's two great discoveries were discovering the photon and in black body physics and discovering Einstein. Planck was one of the key figures responsible for popularizing Einstein and his work. There were some other people who made fundamental early contributions, including Einstein's math teacher, a guy named Minkowski, who came up with the whole concept of space-time. Ironically, Einstein had ditched Minkowski's math classes and had relied on the notes of a really good friend of his. And Minkowski later commented, that Einstein, he was always such a lazy dog in math. I never would have expected him to amount to anything. But he ended up extending upon his students' work and developing our framework for space-time. Well, Einstein wanted to generalize that to studying not just bodies in motion, but accelerating bodies. And that led him to develop the theory of general relativity. And that's that warped space-time that you were mentioning. One of the best explanations of general relativity and how it works is from John Wheeler. And the way Wheeler explained it is Wheeler described it as matter and energy tell space-time how to curve, and space-time tells matter and energy how to move. So that's the interreaction there. Well, as Einstein was developing the theory of general relativity, just like you were saying, he was looking at space and realizing it has this curvature, it has these properties, which kind of smack of being like an ether, like the ether that he had dismissed when he was doing special relativity. And in fact, in 1920, Einstein gave a talk in Leiden in Holland, or I guess Netherlands, in front of Lorentz, who he greatly admired, as one of his intellectual heroes. And Lorentz had long been a advocate of the ether theory. So there's some suspicion, Einstein may have been sucking up to the guy to try to gain his favor. But whatever the reason, Einstein in 1920 gave a speech where he talked about his theory of general relativity, or a lecture. He talked about general relativity, and he explained that the curvature of space looks like an ether. And in that sense, there is some kind of an ether in empty space, the way that space-time curves. Well, fast forward a few years to the mid-1920s, when quantum mechanics was developed, and Einstein was at Heisenberg's first lecture on quantum mechanics in Berlin. And Einstein invited his junior colleague back to his apartment to talk further about these interesting quantum mechanical ideas. We know about this because Heisenberg wrote a book, I think it's Physics and Beyond, that came out around 1970 or so, a good decade or more after Einstein's death. And according to Heisenberg's report, Einstein asked him, well, where are the electron trajectories in this theory of yours? And Heisenberg said proudly, well, there are no electron trajectories. We're only looking at the observables, the initial state, and at the final state. And Einstein objected, well, surely the electron is moving somewhere in the system between that initial state and that final state. And Heisenberg proceeded to quote Einstein back to Einstein and his development of special relativity, and how we should just focus on the observables and not engage in idle metaphysical speculation about what might really be going on. And quantum mechanics, Heisenberg insisted, had to be based on the observables, in exact analogy to how Einstein had based special relativity only on what can be observed, and did away with the ether. And Einstein took a look at that and kind of was a little taken aback. And according to Heisenberg, his answer was, well, maybe I did say that, and maybe I did even write that in my papers, but it's all nonsense just the same. And that was really the break, or at least indicative of the break Einstein had from his original positivistic observables only thinking into the attitude that quantum mechanics should be more than just the mathematical relations between these observables. You know, his attitude that God does not play dice with the universe, that culminated in what to this day is Einstein's most cited paper, one that he did in 1935 with two colleagues, Podolsky and Rosen. It's called the EPR paper, after the initials of the author. And in that paper, Einstein famously argued that quantum mechanics was incomplete and that there had to be hidden variables involved, things like those electron trajectories that Heisenberg had dismissed. So that's kind of the long answer to your question. Well, gee, that space-time curvature, doesn't that look a lot like an ether? The answer is yes, and Einstein himself thought so.
That is a fascinating story. I mean, you touch on so many interesting bits, and I know I'd asked you before if you'd read Lee Smolin's book, The Trouble with Physics, and it's not a deeply important book, except I have just enough. I have a master's degree in math, which is as far as I went in academia, and so I have just enough academic instinct left to try to cite my sources when I can. And it was fascinating when I read it. One of the things that, because he sort of brought up that most of Einstein's work was relatively early in his career, and that later on, sort of as physics moved towards quantum mechanics dominating the social aspect of physics, that Einstein, who wasn't willing to make that jump into that retrenchment from trying to figure out what's going on to shut up and calculate, sort of got left behind. And Smolin, who's a quantum gravity guy, objecting to string theory, is what the book is mostly about. But he brought up a few interesting things, and he sort of touched on them but didn't really go into them. But so I just want to give credit at least for him starting it. And he sort of, and you see that in a lot of scientists' careers, where there's sort of a period in which they're doing the work for which they are best known, and often other work they're not so known for, and he sort of raised the question about, why do you see this, and because there's that popular model of genius, like the Tony Stark model, where you're just a super genius, and anything you turn to, you just make discovery after discovery no matter what and in actual history, people's discoveries tend to be a lot more narrow. I mean, there are people who discover tremendous numbers of things, but they tend to get known for relatively few, and often, and you'll often see like the dominant research going in different directions, and people who are huge getting left behind because they won't go along with it. And it kind of raised the interesting question of like, why do you see that? And a theory he vaguely sort of came near but didn't really spell out is that in some sense that in any given period, the conditions are right for discovering certain things, based on the state of technology and its ability to measure things is kind of dominant in the history of science, as far as I can tell. That when you can measure things, people tend to discover what is now measurable, but before you could measure things that are very small or very faint or very far away or what have you, well, you're not going to do much astronomy without a telescope. And certainly you're going to have a hard time finding out about the Big Bang without a telescope. Anyway, so, and then, interestingly, it seems like in many cases what you have is somebody where, for whatever reason, their interest, their personality, their background, all leads them to think in a certain way that happens to fit the conditions of the moment. And in that moment, they're the ones who, in thinking this way, are the people most likely to use the tools that are just becoming available, the knowledge that's just becoming available, what have you, to make this sort of discovery they make. And then once the things that are discoverable by their personality and their bent and so on in their environment have been made, they're not the weirdo. Essentially they were the weirdo of the day, but then that kind of weirdo will sort of exhaust what's available there, and then you move on to having to have some different kind of weirdo to discover the next thing. So that aspect of it, sort of the history of science, and but so there's that. I'm curious what you think of that, and it also seems to interact with. It's quite possible for the next weirdo to not be going in the right direction, but just to happen to come up with something, to discover something interesting, even if their approach is fundamentally wrong. That a fundamentally wrong approach sometimes is really helpful in discovering something that a better approach would have a harder time discovering in a weird set of circumstances, and that can have the effect of then dragging everybody away from a better approach. So I'm curious in the history of science, as you've read it, how much of that do you actually, how reasonable is that, and how much of that do you actually see?
There are elements of that I think are true. I think a lot of it, though, is the result of wishful thinking and a convenient fiction to convince ourselves that we are rational scientists who are limited only by the quality of the data that we have in figuring things out. And I can go back and explain that. I already mentioned how the work that I'm doing in electromagnetism, really, I'm doing 19th century physics. A lot of what I was doing is just a small step beyond what you will find in Heaviside's electrical papers or in Hertz's electric waves. But it has been forgotten because of ideological blinders and philosophic misconceptions, and the fact that for all of their elaborate, expensive, high-energy particle colliders, physicists have completely lost touch with practical, everyday engineering applied electromagnetism that would give them the clues they would need to really understand electromagnetism and how it works. So let me start with the disconnect between physics and engineering, because I think that's also a very interesting story.
Oh, that's a rich topic. Yes.
Yeah. If you look at what was going on, say, during World War II between the physicists and the electrical engineers, the advanced electromagnetism text was Stratton's electromagnetic theory. Julius Adams Stratton, MIT professor. That's the EMAG book that the physicists at the Manhattan Project and the electrical engineers at the radiation lab building the radar, they were all using that book. That was the common reference that everyone used. Well, you can take a look through that book, and it has a nice selection of practical examples, things about antennas and how they work, and arrays and how they work, and radio wave propagation, and a host of other very applied kinds of electromagnetic topics, at least for the state of the art of the 1940s. Mm-hmm. Of course, that state of the art has advanced far beyond the age of from World War II to today. But if you take a look at the physics textbook that is used in graduate school, the most common one is by Jackson, Classical Electrodynamics. I studied it out of the second edition when I got my PhD. I think the third edition is the standard book that most graduate programs are using today. You can go through the table of contents of Jackson and compare the topics from Stratton And what you will discover is that Jackson presents an atrophied and dumbed down version of the applied topics that were present in Stratton. So what that means is today's physicists have a more meager, a poorer understanding of applied electromagnetism than their predecessors of 80 years ago. That was really kind of shocking for me when I realized, oh, that's a big part of what went wrong, because there's been a lot of progress in our understanding of applied electromagnetism. Concepts like impedance, which is just barely touched upon in Jackson, but is fundamental to understanding transmission lines and how they work, and things like transmission and reflection coefficients and doing antenna matching. And physicists wouldn't know what a Smith chart was if it hit them in the face. Things like antenna theory and understanding the physics of electrically small antennas and all the theoretical progress in understanding what's the relationship between the bandwidth of an antenna and how efficient it can be. And very few people, if at all, have tried to apply that to understanding atomic physics, which they really should do, because it's a very common, there's some commonality in that issue there. So what we have is a situation where today's physicists have really lost touch with the applied electromagnetism and the facts that they would need in order to understand what electromagnetism is and how it works. Now, you can look at Jackson, and there's plenty of stuff on, particle accelerator radiation and Bremsstrahlung and all of these exotic things that would be of interest if you want to build a particle accelerator. But the stuff on antennas, again, it's a dumbed down version of what was in Stratton, with maybe half the content that was in Stratton gone and missing in action from the conversation. So that's one key fact, the disconnect between engineering and physics and understanding electromagnetism.
Can I interject a quick question?
Oh, I'm sorry?
Forgive me. Can I interject a quick question?
Sure.
Before it gets lost. The academia being accused of being in an ivory tower disconnected from the real world is a very old one. But what you said before, actually, about the, that approach of stop asking what's actually going on, and instead the shut up and calculate. Right. Does the thing that you're describing, do you think that's sort of part of that culture of, well, the real world is stuff that's actually happening is not really pure idealized physics. It's messy. It's philosophical things that actually happen, but it's not all the pure. Do you think that I'm not phrasing it very well, and pardon me, but do you think that that's partially a result of that culture of don't ask what's actually happening, and things like how do antennas behave is stuff that actually happens?
Well, yeah, that's probably a large part of it. I mean, I think the sense in physics is Maxwell's equations. We've known that for 100 years. It was very interesting to me as I started trying to publish papers in this area of, here's what went wrong with electromagnetism, and here's what we need to do to extend upon electromagnetism and improve it. You can go to archive.org, the website where it's kind of a clearinghouse for physicists to share preprints of their work. And they don't have any category to share, hey, I found something new in electromagnetism that I'd like to share with you. I mean, you have to go to general physics or history of physics or something like that. I mean, they have topics in solid state or particle physics where electromagnetism comes into play. But if you want to say, hey, I've got a cool new way of expressing Maxwell's equations, or look at how this practical antenna system helps us understand what's going on in electromagnetism. I mean, they have no idea what to do with that. In fact, I tried submitting papers there, and they would not accept my papers. They didn't think I was a real physicist, probably based on the topics that I was addressing. But a big part of it is the whole positivistic trend in physics thinking that was popularized in the development of quantum mechanics, not only by Heisenberg, but even more importantly by Niels Bohr. Of course, Heisenberg was responsible for introducing a lot of that observer-first attitude into quantum mechanics, but really, the person most responsible was probably Niels Bohr. And he had a lot of ideas about things like complementarity. He argued that when we have a paradox, that is evidence that what we're really dealing with is a great truth, like the whole concept that it's a wave and it's a particle at the same time. Well, clearly that's contradictory, but because it's contradictory, that's how we know we have stumbled upon a deep and profound truth. It's very tough to get a handle on Bohr and what he really thought, because he didn't write things down and was not at all clear about what he meant. But ironically, he was so vociferous and so aggressive in sharing his perspective. I mean, at one point, Schrodinger visited the Copenhagen interpretation, and what the climate or allergies or whatever, he got kind of sick and had to just stay in his room. And Bohr hounded him on his sickbed, browbeating him to try to get him to reject the wave theory of quantum mechanics. All the while the guy's running a fever and feeling miserable and just wanting Bohr to go away. Just to show the energy with which Bohr advocated his perspective, the particle physicist and Nobel laureate Murray Gell-Mann argued that Bohr brainwashed a generation of physicists. And I think that's really true. And there are, well, let me share some of the stories that you will find in various physicists' memoirs about what happened. Now, at the Solvay conference in 1927, Louis de Broglie tried to introduce his pilot wave theory of quantum mechanics. And he basically got argued down by Bohr and by a lot of Bohr's supporters, to the point where de Broglie was convinced, oh, well, I must be wrong. Everyone thinks I'm wrong. I'll move on and do something else. And in fact, John von Neumann, the famous mathematician, wrote a mathematical proof that there could be no hidden variables in quantum mechanics, and therefore we had to just adopt the Copenhagen interpretation of quantum mechanics. Well, fast forward a couple decades, it's the early 50s, and a young physics professor who's just been hired on at Princeton named David Bohm decides to write a quantum mechanics textbook. And he writes what many people would regard as the ultimate explanation of and discussion of the Copenhagen interpretation approach to quantum mechanics. But as he's doing it, he's got questions, and he starts digging in and trying to figure out what's going on. And he comes up with this idea that we could treat waves and particles differently. He basically rediscovers de Broglie's pilot wave concept and starts writing papers about it, and shows that, well, von Neumann's wrong. The theory works perfectly with regular quantum mechanics. We don't have to be making these there's nothing going on assumptions. We can assume that there are waves guiding the particles as they move through our quantum mechanical systems. Well, he had to flee the country because of concerns about his communist sympathies, and ended up in Brazil. And J. Robert Oppenheimer, who of course was the Manhattan Project director, and in the mid-1950s, he was the director of the Institute for Advanced Studies at Princeton. He assembled a conference where he got together all the best scholars that he could get, and their grad students from Princeton, to put the Bohm-de Broglie pilot wave concept to rest, drive a stake through its heart so people would just stop talking about it. So they spent all day looking at how they could go about proving that it had to be wrong and wouldn't be acceptable. And at the end of the day, having failed to find any way to disprove the theory, according to one participant, Oppenheimer said, well, if we can't prove it's wrong, we'll just have to agree to ignore it. And that's really what they did. I mean, there's another story that before this, Oppenheimer went to one of his grad students and said, here's this pilot wave stuff that Bohm was doing. Go prove this wrong and come back to me next week. And the graduate student came back next week saying, well, I can't find anything wrong with it. It works. And Oppenheimer said, well, I'll do it myself. And he started working through it. And he couldn't find any justification for arguing that it had to be wrong either. And then you led to that ultimately to that seminar. And you hear these stories, and it sounds so ridiculous that any scientist could possibly have that kind of attitude. And I'd be kind of skeptical. Of course, these are all second and third hand accounts, and you never know if someone's kind of shading the facts and the account of what happened. But I have a firsthand experience with this because when I was in graduate school, one of my advisors was John Wheeler. And he studied under Bohr. He was the professor who hired David Bohm to Princeton. And as I was studying quantum mechanics, I came across the pilot wave theory, and I thought, wow, this explains everything. This makes so much sense. So I waited for my next opportunity. I went in and I talked with Professor Wheeler, and I asked Professor Wheeler, Professor Wheeler, what do you think of this pilot wave theory from Bohm and de Broglie? And Wheeler said to me, the screwdriver theory of quantum mechanics. And I wasn't entirely sure what he meant by that. I kind of guessed, I'd seen people criticizing it. Oh, this is just a arbitrary reactionary physicists putting epicycles into quantum mechanics that don't have to be there because they just can't accept the wisdom of the Copenhagen interpretation, and they're bitterly clinging to their classical notions of causality. I mean, arguments like that. Yeah. But I didn't understand what he meant. He was so dismissive of it. I was a little afraid to ask further. So I said, well, Professor Wheeler, and he had written books on quantum measurement theory and lots of things on quantum mechanics and how it works. I said, Professor Wheeler, well, is there some place I can go in your writing, a paper you've done, or someplace in one of your books that I could look at to further understand why you don't see any merit in the pilot wave approach? And Wheeler kind of looked aside, and then he looked back at me and he said, I really ought to look into that sometime so that I can know what's wrong with it. He was taking it for granted. He'd never looked into it himself. Bohr said it was nonsense, and Bohr is the founder of quantum mechanics, and everyone treats what Bohr says with reverence. And he never bothered thinking through it himself. And I think there were a lot of physicists, at least of that era, who were convinced, it has to be wrong. And someday when I've got an afternoon to spare, I can sit down and I can just work through, and I'll be able to prove it's wrong because it's so obviously wrong. It can't possibly be true. But I won't take the time to do it myself because it's so obviously wrong. Why waste the time proving it wrong? I mean, it was this groupthink that really kept physicists from taking it seriously and from exploring causal theories of quantum mechanics. And that was the big connection that I made was, I'm studying electromagnetism. I'm realizing that if you want to understand how electromagnetism works, classical electromagnetism, forget quantum mechanics, just go back to 19th century electromagnetism. How does the Poynting vector and the Poynting Heaviside theory of energy flow work? Well, very clearly, it's waves guiding the energy. So for instance, I can give you a simple example. If you have two plane waves that pass through each other at the speed of light, normally we'd say, well, nothing happens. But if you study the energy flow, if the waves are the exact same shape, they're going to interfere with each other. If they interfere constructively, then what will happen is as they superimpose, the energy becomes electrostatic. If they interfere destructively, the energy becomes magnetostatic. But either way, the energy comes to a rest, changes direction, and goes the other direction. So if you have a forward and reverse wave passing through each other, and they're identical in amplitude and shape and so forth, they'll trade energy. So it's a very clear and simple example of the fields doing one thing, just passing through each other at the speed of light, and the energy doing another thing. The energy bounces, in effect, from the energy in the other wave. And and that's just one example. There's example after example after example how the fields are guiding the flow of energy, but from start to finish of an electromagnetic process, the fields are guiding different energy. The energy is taking its own course under the influence of the various fields that are in the system guiding it. So I looked at that theory and I realized, what I found is a classical justification for why pilot waves has to be the fundamental theory of, or something very much like pilot waves, has to be our fundamental theory of quantum mechanics. So that's what's led me. That was the conclusion of this quest I've been on, trying to understand electromagnetism.
That is really fascinating. And one of the things that's kind of interesting that you touch on, there's a fundamental epistemological problem that all people have when it comes to experts, which is, how do you know that somebody's an expert? And somebody else tells you, okay, well, but if my friend who doesn't know any more than me about the subject tells me that he's an expert, well, how does he know?
Right.
And you can kick it down, and you really do actually hit a basic fundamental problem that you have to. Well, there are two solutions to it. One of which is you have to be able to evaluate everything the expert can do yourself, in which case you can only evaluate people who are equal to or less of an expert than yourself. Right. Or the other one is, of course, when people can produce results that require expertise to produce, which is the kind of the motivation. I recently, I have no idea if you saw it or not, but I recently put out a tweet saying that if a person's experiments have not been verified, or have not been duplicated by others, then we have no idea whether or not they're any good at doing experiments. The one thing we do know is that they're good at getting funding.
Well, that's the prime characteristic to get a job in academia.
And it's something, having looked at academia and looked. I mean, I was in mathematics, not in the sciences, but I knew enough people, and heard enough things about how things work to understand that sort of the primary job of a primary investigator within a lab is securing funding. Right. And they do occasionally do some science too, but their main job, their primary job, is that funding, because without the funding, there's no lab. Right. And it's funny too, because this touches on another thing. I always say that people never take the idea of evolution, seriously enough. That is to say, they never take the idea of selective pressures in an iterated environment seriously enough. Because, of course, publish or perish is a selective pressure. And what things lead one to publish? Because if you don't, you will perish. So what things lead to publishing? And one of them is having, important and good things to say. But there are other things that will lead to publishing too, and more reliably, because having important and good things to say is hard. But, I once joked that one of the fundamental principles of science, more properly like academic science, is to assume anything necessary in order to publish. Mm-hmm. And which you see all over the place. Things are. I've looked into a lot more nutrition papers. Physics, I've only sort of read popular books about to understand, and you see very much where people will take the attitude of, well, if there isn't good evidence available, then we'll just have to field promote bad evidence to good evidence so that it can be it's the state of the art, even if it's terrible evidence. You've got the world's worst study that proves absolutely nothing, but well, you don't have anything better, so we're going to have to treat it as if it was good evidence so that we can actually have things to say. And then there becomes the interesting iterative question of who will become grad students to such a person. And then when they become professors, who will become grad students to somebody who is willing to be the grad student to a professor who's just going to field promote terrible evidence in order to have something to say. And there's an interesting iterative process to that as you sort of work it through. And we're at academia in its present form is recognizable for what, 150, 200 years, something like that, like where people really have careers in academia in the modern sense.
Well, a lot of it's interesting how recent a lot of our contemporary concepts of science are. It's also interesting where some of the deep roots of it are. You can take a look at Francis Bacon and some of his writings, and in particular, The New Atlantis is a good summary of this. It's a novella. It's like a science fiction novella where he describes voyagers coming on this hitherto unknown land where the people have an institution they call Solomon's House, where all of the scientists sit, and they are provided with all of the best facilities that scientists could possibly want to have to do their investigations. And they have a huge staff with elaborate division of labor where some go and gather intelligence from other nations about their science, and some set up experiments, and some perform experiments, and some take the data from the experiments, and some analyze the data from the experiments, and some review the analysis of the experiments and come up with new experiments, and so on and so on and so on. Just this incredibly elaborate division of labor that Bacon describes. And then when they come up with scientific discoveries, the scientists think carefully about whether they should tell the government about what they've done, or if it's better to just keep it secret to themselves. And if someone has made a discovery, they'll make a great statue and honor them and give them money. And you read this, and it's a scientific bureaucrat's ideal utopia of being honored and recognized and in charge and getting all the resources you want to do things. And it's all the institutionalization of Bacon's concept that to command nature you must obey her, and that science is the means for securing secular power in the world and being able to advance the cause of humanity and engage in life extension and curing diseases and so on and so forth. And what's interesting is when the Royal Society was founded in, I guess, around 1660 or so, when Charles II was restored to the throne, not 6 or 7 years later, the history of the Royal Society was published. You wouldn't think they'd had that much history in the 6 years, but they were enthusiastic, and by God, they were going to publish a history of their 6-year-old institution. And the person that they credited as the author of the great enterprise was Francis Bacon, who'd been dead for 40 years or so by that point. And you can see the frontispiece of this history that is just overflowing with Masonic symbology, from the black and white checkered floors to a half dozen different squares and compasses in obtrusive places hanging on the walls and so forth. But that really, and of course, Freemasonry didn't become out and public until I think 1717. So it's very clear that it was tied up in the Royal Society, and that the Royal Society had a Freemasonic affiliation back in the 17th century. But anyway, that institutionalization of science by the state, and that concept of technocracy and bringing to our modern day scientism and trust the science. But it's fascinating how the details of those rituals have only really been finalized recently, like peer review, for instance. Now, Einstein got through an entire career without ever having his papers reviewed, except for one time. And the one time the editor of Physical Review had the audacity to take the paper Einstein had entrusted with him and hand it out to third parties to get comments, Einstein was so offended that he refused to publish ever. He withdrew his paper, and he refused to publish ever again in Physical Review once he found out. But physical review, or the process of peer review, only really became common once Robert Maxwell, who is the father of Ghislaine Maxwell, the collaborator with Jeffrey Epstein in their wrongdoings. Robert Maxwell bought a scientific press that became Pergamon Press, and started the ingenious, if somewhat dubious, business practice of multiplying a variety of journals, so that there would be all kinds of journals on every kind of subject. And in the past, you'd have a few really brilliant editors who were masters of their entire field and could look at a paper and say, yes, let's publish this. No, let's not publish that. But now, with all of this proliferation of journals, Maxwell needed some way to get the papers evaluated for publication, and he and his editors came up with the idea of peer review. Just take them, send them out, see what a couple experts say who are reviewing them for free. Review their comments, make the decision based on those expert comments. So you don't have to be quite as much of an expert. You can just trust the other experts that you've given the paper to. Charge the author page fees for the privilege of having their paper published. Charge the university hefty subscription fees for the privilege of being able to keep up with the state of the art and the latest discoveries. I mean, it's an amazingly, hubristic business model, but man, it worked, and it really established peer review as being the touchstone of high quality science.
It is hubristic. It's also got a lot of insight into people, because something I've wondered, Harvard, which is in the news lately for various reasons. For example, their deep moral principles to discriminate against Asians being the one I'm thinking of. But the thing, I just sort of idly wondering. So I've heard about Harvard as it's an incredibly prestigious university, and then I wonder why. Why is it prestigious? And I mean, one thing I've seen, one thing I do know about Harvard is that if you ever encounter a graduate of the Harvard Divinity School, you can assume they know nothing about theology, or that everything they know is wrong, essentially. But so there's that they really have a amongst anybody with any sense, Harvard Divinity School, it's just the Harvard Center for Atheism, and I kind of vaguely aware of that, and then wondered, and as far as I can tell, it's basically like lots of rich people would send their children to Harvard, and that I think, and this is my suspicion, and I'm. There's a healthy amount of a healthy fraction of what I'm saying is speculation. So to be upfront with that, but it seems to me that you get a lot of that. You get people who have graduated from it, who have positions of power. Wealthy people would send their children there, and that's all of the hallmarks of status within human beings. You have wealth, you have power, and this is in heavy association. And it strikes me that the thing you just described about the journals and the charging everybody lots of money is actually really very insightful into human psychology, because if you charge everyone tons of money, then they assume it must be prestigious. And every university that pays the enormous amounts of money gains in prestige from having access to this very expensive thing. And everybody who's there can say, I'm reading this thing, and if you want to read it and you're not here, well, you'll have to pay enormous amounts of money, and you can't do that, so I have access to what you don't.
Right.
And that's, so I mean, I guess, credit where credit is due, that there's some pretty good insight into human psychology there.
No, I think that's a fair statement.
Which sort of brings up that interesting topic that we've been talking about, the nature of that if when somebody has prestige, and prestige is really a social thing. Prestige is to some degree, the degree to which people will defer to a person. And, I've seen Andrew Streltsky, a friend of mine on Twitter, describe it as prestige is the degree to which you anticipate other people will defer to a person. And that's a very I think there's a lot to his definition there. But the thing missing, of course, is knowing that a person is actually extremely good at what they do, which, of course, you only really can do if you're at least as good. In which case, your judgment of somebody else's prestige is only good up to your own level of competence, essentially. And since prestige is all about people who are more competent than you, there's kind of a fundamental practical problem with the nature of prestige. But we're social creatures, and we need to be around each other. We need to feel respected, and it's really dangerous it can at least feel really dangerous to stick your neck out and to stand up and be saying something different than everybody else and the people to whom they look up. And so but it's very interesting, the history that you're describing. And it is, did you go into that in the book? Essentially, like, the power of a person's personality to, like Bohr, to wrench everybody away sort of by force of will or power of personality?
That's more a topic for book 2, where physics went wrong. That starts at Mach and positivism and runs through, really, Einstein is the central character in book 2. And it makes for a fascinating story. Of course, I'm a science fiction author and novelist as well. So I liked the dramatic nature of Einstein's narrative arc, where he, if you want to point to one person who destroyed modern physics, he'd be your culprit. Now, he had a lot of help, but he was the one who really got the ball rolling. And then all the different waves of publicity of people publicizing him because it served their interests for one reason or another. And then the mature Einstein looking at what he had wrought and deciding he wanted to get off the train because it was nonsense, and trying the best he could for the rest of his career to try to rein things in and come up with a more reasonable answer, and unfortunately ultimately failing.
That actually reminds me, I'm curious if it does you too. There's an interesting thing you see when you see like people who are media figures who are sex symbols, especially, where when they're young and very attractive and have terrible judgment, then they are happy to use the attractiveness of their body and personality to sell things, and especially often connected with hedonistic messages and so on. And there are people with money who will use them in order to make lots of money and promote them and use that money to bring them to people's attention. And there's a very synergistic thing because there's a huge audience for being told, for looking at people often with less clothing than really they should be wearing in public, for getting told all about that life is really about pleasure and so on. There's an enormous appetite for being told that satisfying your animal instincts is the height of happiness. So there's huge market money to be made from this. And then the person sort of does this for a while, and then they age out of that because they finally gain some experience of the world and realize that, like, actually this is pretty bad. But at that point, they're no longer serving the interests of people who make them popular, and they're also not saying anything that audience who just wants to be told that life is all about eating, drinking, and being merry. And so once they have the experience to know that this is a bad idea and sort of step out of that role, they're not in a position to influence anybody. They have neither the support nor the interest. The audience that they had cultivated is no longer interested in hearing is never interested in hearing anything better. And so I'm curious, what do you think of that analogy to that arc of Einstein?
Well, I think there's certainly some parallels to what you were saying, and this is something now. Just to be clear, I am serializing my book on my Substack. It's at etherzar.substack.com, and
links in the description.
All of the all the material from book 1 is already up there. I've made some edits as I'm compiling it and getting ready to release book 1 here in another month or so. And a lot of book 2 is also up there, including a lot of the story of Einstein and the publicity machine that made him so popular. there was enormous controversy around Einstein, really from both angles, from the people who were publicizing him and the people who were trying to tear him down. And it's fascinating to go back and look at the propaganda and see how completely over the top and heavy-handed it was. But how we can see that from our more jaded, cynical, modern perspective, since we live in a world saturated by sophisticated propaganda. Back in the 1920s, this was brand new, and it was crude and it was simplistic. And it was very easy to see exactly what was going on. And you have to understand the sensibility of the time. Einstein's friend Max Born wrote a popular, no, I guess it was a textbook on relativity. And of course, he wanted to put a picture of his friend Einstein as the frontispiece for it. So you'd open the title page, and there, facing the title page to the left would be a nice professional black and white picture of Albert Einstein. Their mutual friend, Max von Laue, was appalled at the shamelessness of this promotion of putting a photograph of a living scientist in a book about the scientist, and how completely unprofessional and uncouth that practice was. And Born, kind of taken aback, pulled the photo from the future printings of the book. Well, at the same time, as Einstein, the 1919 eclipse was taken as validation for Einstein's theory of general relativity, and there was enormous publicity about it. With just completely over-the-top publicity of Einstein, on par with Newton and Galileo and Copernicus, the greatest thinker of our time. Scientists are agog with his great discoveries, and has obliterated and destroyed our concept of absolute space and time. Just amazing over-the-top kind of stuff. And that caused a lot of negative reaction, because for the time and for the mores, that was just almost an obscene level of narcissism and promotion. And there was a back reaction to it that also tended to feed off of some of the anti-Semitic currents that were present in society. And that started this whole controversy around Einstein's Jewish physics, and Einstein and some of his backers dismissing what are really legitimate criticisms of relativity, saying, well, if you disagree with Einstein and with relativity, you're clearly anti-Semitic or ignorant, or both. It's either one or the other or both. And Einstein said as much in a newspaper interview when he came to America in April of 1921. But that publicity campaign was just amazing. I tried to track down the details of how it was organized, and I strongly suspect that the famous father of public relations, a guy named Edward Bernays, was involved in the Einstein publicity campaign. And that's something I go into in a couple of pieces on my Substack, how he was associated with Chaim Weizmann, who was the head of the World Zionist Foundation or organization, and how Weizmann and Einstein came with a party to raise funds for the National Hebrew University, and how there were massive crowds of mostly Russian and Eastern European Jews to welcome the party. They were there to support the Zionist mission. But reporters who were there, who weren't clued into the whole Zionist thing or having any idea who Weizmann was, they hadn't heard of Weizmann. But that Einstein guy, he's the guy who discovered general relativity. So they assumed the crowds were all there to see Einstein instead of Weizmann, and that kind of kicked off a whole wave of publicity, because the more establishment Jews who owned like the New York Times and other major media organizations, they were not. They weren't in favor of the more aggressive Zionist goals of having a state in Palestine for Jews. And so they were quite happy to also say, oh, yes, this is all about Einstein. And don't look closely at those Zionists whose message we don't approve of. All these people cheering, they're there for Einstein because they respect great science. I mean, it was just amazing seeing all of the undercurrents of the propaganda and the hidden agendas that the various players in pushing and promoting this had at play.
That is interesting. I'm curious too. So one of the biggest things, societally speaking, within the social attitude, a thing impacting the social attitudes towards science, was the development of the atomic bomb. That I especially, it's a thing I suspect a lot of, interestingly, like a lot of younger people I think don't appreciate as much in the time period. But I mean, I'm in my mid 40s, and I remember my parents talking about this all the time, about the and my grandparents, the tremendous, the degree to which the atomic bomb just filled people's consciousnesses. And also, with regard to science, that here's something, to my knowledge of history, very rare, which is you get together a whole bunch of scientists, and then you have they develop a power that simply dwarfs mechanical power before it. That the atomic bomb simply dwarfs all bombs that anybody had ever made before. And that leap in power, that godlike power in the little g sense of God, like the powerful entities, powerful beings living in the world. They're just much more powerful than human beings, but not God in the sense of the, subsistent, being upon which all moments are contingent, etc. That human beings become like gods, able to destroy an entire city in one go, all because of the scientists who had been gotten together. So that seems, at least to me, to have had a huge impact on the social aspects of science, and to have been a tremendous social, as far as the social perception, that the physicists who were involved with this, obviously, these again are like gods among men, able to bring down the power of the gods to human beings. So I'm curious, in terms of your perspective now, of somebody trying to do science and trying to explain what actually is discover what is the world. Do you see reverberations of the Manhattan Project in attitudes about science, or is that more popular but less in the actual practice? Or
Well, it certainly led to a great institutionalization of science. And I think it led to a great centralization of science. On the one hand, science had demonstrated its ability to serve as agents of destruction, and not just with nuclear weapons, but with things like radar, which arguably was a greater technological advance and more significant to World War II than even the atomic bomb, and other great advances of the period. And because of that destructive capability, there was a great desire to kind of keep it under control. So the National Science Foundation, for instance, was set up at about that time to try to nurture and fund science. Science was the weapon of geopolitical hegemony and dominance. So, we had to have science, and by God, our science had better be better than the other guys if we want to win the next war. So there was an element of that, but there was also an element of, we better keep an eye on what these pointy head, four-eyed guys are doing, lest they come up with some other kind of atomic bomb without us realizing what's going on. So I think that there was a great deal of centralization, control, and support. And part of the problem is it's enforced a kind of groupthink in science. Because everything is so centralized, because any significant amount of scientific funding is going through these peer-reviewed channels. If you want, like you were talking about, the art of being a great scientist is the art of being able to secure funding for your team. And how do you do that? Well, you go to the peer review community that is responsible for deciding whether funding will be dispensed to you, and you give them what they want. You show them modest improvements and extensions upon the ideas they already accept. Here's the stuff that you believe in, that you do. We're going to do it just a little bit better, and here's how, kind of work. And if you come to them instead with a story of, all this stuff that you've been doing in your career, we think it's wrong, and we have a different idea, and we want to try this instead, that's a lot less likely to get funded, and you're a lot less likely to be successful because of it. So, yeah, the centralization of support that was engendered after World War II, I think, has contributed greatly to the groupthink in science. There's this fascinating, I don't know if you've ever looked at Herodotus and what he had to say comparing Egyptian and Greek civilization. What he pointed out is, the Egyptians had this great ancient civilization, but it was monolithic, and it was not very creative. It was the same a millennia later as it was a millennia earlier because of that centralization. The Nile River Valley supported such easy transportation that it was very rare for Egypt not to be united under a single pharaoh and under a single pharaoh's control. And you can compare that centralization and cultural stasis to the situation that happened in Greece, where you had many competing political entities separated by valleys and mountains and different places along the Greek peninsula that you could only get to, practically speaking, by boats and so forth, and how that competition between all those competing political units led to Greek creativity. And that's something that Michael Crichton also pointed out in, it's not Jurassic Park, I think it's Lost World, one of his novels. He has one of his scientist characters pointing out or arguing that the internet is the death of creativity, because now everyone is going to think alike. Everyone is seeing the same thing. Everyone has their McDonald's and their the same music and the same movies that we're all watching. It's all centralized. It's all monolithic, and that's going to kill our creativity. Now, I think that that's probably wrong, because the internet has also allowed the creative outsider to be able to reach out and communicate and get around the gatekeepers. It's easier to do that now than it ever was. I mean, 20 or 30 years ago, if you couldn't get your paper past a journal editor, you were pretty much stuck. I mean, maybe you could go and give some talks at a university, but you'd be talking to a few dozen people at a time and hoping that one or two of them might like what you have to say. And then you're on to the next university, having lost contact with the potential converts you made earlier. I went through that process trying to push and promote my ideas. I made a deliberate effort to give talks, and I spoke at everywhere from on the West Coast at USC and UCLA. I gave talks in Texas, in Indiana, in Virginia, of course, in my home state of Alabama. I even gave a bunch of talks in England about my ideas, and I still did not get much traction. I finally got a paper published in a pretty respectable peer-reviewed journal in the Philosophical Transactions of the Royal Society, summarizing my ideas. But The problem is there's so many papers coming out and so much noise out there that one paper just isn't going to attract a lot of attention. And I was really frustrated at the difficulty I was sharing what, from my perspective, was just such a powerful and simple and obvious idea about electromagnetism and how it works. I was discussing this with a gentleman who I think is a mutual friend, John C. Wright, and his wife, science fiction grandmaster, and was explaining my frustrations. And John C. Wright asked, "So what is this cool idea of yours?" And I explained it to him, and he and his wife Jaji just got it, and the light bulb turned on for me at that point. That my problem wasn't that my idea was so complex that it was difficult to explain to physicists and engineers in academia. My problem was it was so different that they couldn't really, it was very difficult for them to step out from their premises and consider a fundamentally different perspective on things. And that I'd be better off making my primary thrust trying to talk to curious students and intelligent lay people instead of trying to address the academicians in the ivory tower. And that's what my Fields and Energy project has been about. And I'm really gratified by the response I've gotten. I have something like almost 3,000 people subscribed to my Substack. And this is a Substack on electromagnetism and the history of science. So I mean, there's a lot of interest in it. I've never in my life addressed an audience that big just going to a technical conference, for instance. And so the internet has given me the ability to share and spread my ideas with a really pretty respectably sized community of people who are interested in hearing what I have to say about it. So I really think Michael Crichton was wrong, and that the internet. There's obviously dark and malevolent forces at work who are eagerly trying to turn the internet into a tool for totalitarian control and implementing things like digital currencies and controlling what you're allowed to spend and monitoring your behavior and making sure that you can't do things they don't want you to do and so forth. But at the same time, that ability to reach out and to talk and persuade and to build a community to talk about your ideas, it's immensely powerful, more so than at any previous time in history, as far as I can tell.
That certainly seems to be the case, the ability to find other people and build, because ideas need you need a nucleus, but the nucleus of people that you need doesn't seem to scale so much with the size of your civilizations to just be a constant for human beings. And as long as you can find a group of people, and the critically the right group of people, to work together, that's what allows people to really develop things. And the internet, it lets you find those people in a way that was much, much harder, and does seem to somewhat get around that problem. I forget who it was and I don't know the degree to which it was a joke when it was said, but the famous phrase that science progresses one funeral at a time.
Yeah, that was Max Planck, and I think he was probably right.
And so it lets you get around that problem because you can talk to people without them be the people you have to wait for the funeral being in the way.
Right.
And so, and to some degree, it's fun. It's interesting what you said about archive.org, because I'd heard about archive.org as actually being a major step away from the super centralized gatekeeping. That so it's and of course it's natural enough that people will always want to be the gatekeepers, and there are people who very much want control over others, and anytime you have any centralized anything, they will always seek it out. So it's a fundamental constant of human history is that there are people who want power, and anywhere where they think they can get it, they'll show up. So I mean, we'll never be without people who want power over others, so it'll be a continuous problem. But all the same, it is. I think you're right about the internet in that regard. That it lets people find each other, lets people find things. For various reasons, I've been interested in nutrition, and many of them highly practical reasons. What with me being a person who eats, and I've looked into and looked into the state of science. I mean, that's where I've read the most scientific papers is in nutrition, and it's a in many ways a particularly bad field. To be fair, it's also a virtually impossible field because to do a proper controlled experiment, you need to get a bunch of people and essentially lock them in some place and control everything that they eat. And then even if you do this, which nobody can afford to do this for more than a few weeks, metabolic ward studies they're called, well, you're not studying people who are actually living a normal life, and living a normal life involves doing things that rely upon the nutrients that you're taking in. So you're not even studying people in the environment in which you want to apply these things. So your ability to perform controlled experiments is effectively zero.
Well, I can tell you that I tried to be a subject in an experiment like that during my graduate school days. And the way the experimental protocol worked was they would allow you to live your life, but you had to eat precisely the meals that they gave you. And then you had to do stool samples and turn in your stool samples. They basically said, if you cheat, we will know, and then we won't pay you anything. So, but the basic idea was, they'd give you their, the peanut butter sandwich and, whatever. I mean, there's a whole bunch of very bland food that they were giving. And then I forget exactly what the treatment was for the people outside the control group. But yeah, it's a difficult thing to do, and you have to count on your subjects to have the discipline not to snack on unauthorized food while you're feeding them a very monotonous and bland kind of diet.
You do, and to do it, what's particularly bad, I mean, you see the same problem in global warming, because right, the proper way to determine whether or not anthropogenic global warming is happening is you have a control Earth and an Earth where you add carbon dioxide, and then you run this for 100 years and you see what happens. There's some obvious practical problems with this, so you don't have any sort of good the ability to perform an actually good experiment. And nutrition has that same problem. So it's a particularly bad field, but sort of because of that, it's actually a place where you get to see an awful lot of there are people who have their motivations. There are a ton of I would call them evangelical vegetarians, but they're not trying to spread the good news. They just want to sort of force vegetarianism on people. They don't really want to convert people exactly. They're relying on trying to convert people because they just can't do what they actually want to do. But I'm sorry, I'm getting a bit too much into the weeds there. Point being that it is a really good place to see the social effects, and especially the effects of the people who are providing funding get to say what their money is used for. And if absolutely nothing else, if you have a massive source of funding, even if everybody's on the level, and there are plenty of people who aren't in the world, but even if everybody is on the level, they're channeling this funding to one particular set of experiments, to one particular kind of thing, and that means that you get a lot more of it. And so this will just, by sheer volume, tend to dominate the literature involved. So it's... then you throw on other things like you can halt experiments, they look like they're not turning out right, etc. So it's a very imperfect world. But so I've seen that, especially, sort of looking closer there, the social effects of it. And so I guess I'm especially looking forward to volume 2. Although,
Well, as I said, a lot of volume 2 is already on the Substack. You just have to go reading the back posts about, Einstein and his trip to America, and the problem of what were Einstein's references, and was he a plagiarist, and things like that.
Yeah, I have to admit, there's something to me about paper, being able to hold stuff in paper. I'm one of those odd. I mean, I have ebook readers, but all the same, I still just love paper books. But not to say I'm not going to check out your Substack, because I'm also impatient. Um, but getting to the just briefly, because we've been talking for a very long time now. But just briefly, so, getting to the initial history of electromagnetism, would it be fair to say that it was dependent upon the discovery of, well, electricity started with the voltaic pile, right?
Right.
That was the beginning of actually being able to make electrons flow through a wire. So,
Well, that electrons flowing through a wire actually goes back, a good 100 years before that. That was Stephen Gray, and in the early 18th century, who did the first experiments of trying to make electricity go from place to place. As early as the 17th century, people were making frictional electrostatic generators to collect electricity and then to store it in Leyden jars, basically big capacitors, and then doing experiments with charging things up and looking at electrostatic attractions and things like that. That was a big emphasis in 18th century science, and when Franklin and others took those early results and kind of developed our modern theory for electricity. But yes, it became a lot easier to do experiments after Volta came up with his voltaic pile, the first battery, and you could actually get DC current for once instead of having to rely on a transient discharge from a Leyden jar.
so do you cover that?
Yeah, that is in book one, all that history of how electromagnetism was developed. The first chapter is kind of introductory and talks about models and how they work, and kind of introduces some of the concepts that are needed in order to navigate your way through everything that follows. The second chapter traces development from Aristotle and Plato through medieval physics. I focus in particular on Aquinas and Roger Bacon and Robert Grosseteste. I have a big section on Francis Bacon that I've already talked about, and his influence, not so much on science, but on scientism. And then talking about Galileo and Descartes and Newton, and a lot of the early electrical pioneers like Degulier and Dufay and Nollet and Stephen Gray, leading up to people like Franklin and Priestley and Coulomb. I just finished the index, at least a rough draft of the index earlier today, and I have over 600 people cited in separate names in the index of names in the book. So I've got a lot of coverage discussing all of the people who were involved in the origins of electromagnetism, and and historians who commented on it, philosophers and so forth. So I take the story all the way up to Faraday and Maxwell and Heaviside and Hertz, to the end of the 19th century and the development of classical electromagnetism, Maxwell's equations, Hertz's discovery of radio waves, and the Poynting-Heaviside theory of electromagnetic energy flow. And I just kind of present the basics of that and how it works, and the difference between fields and potentials and how fields behave in kind of a simplistic fashion. I just wanted to get the basics, the fundamentals and origins of it. Book two will cover where physics went wrong and takes Mach and positivism as a starting point and traces Einstein's career through relativity into quantum mechanics, how quantum mechanics developed, and Bohr's influence in kind of keeping the intellectual blinders on quantum mechanics as we move forward. And then finally, in book three, I will talk about taking all of the applied engineering electromagnetism that has been overlooked and ignored by physicists, and show how that leads to the fields and energy approach to electromagnetism that I advocate, and how that plays out. And the book three is organized starting with simply with just waves interacting with each other, moving through into a study of optics and light, and how and antennas and transmission lines work, and finally talking about quantum mechanics and how this applies to a more pilot wave interpretation for quantum mechanics. So that's yet to come. I haven't had a chance to serialize the book 3 content yet, but most of the book 2 content is already on the Substack.
I don't know if it would count as a spoiler, but will you discuss at all the concept of virtual photons? Because that's something I read about just a little bit, and it's one of those ones that makes me kind of look at it and just immediately ask, could that even possibly be real?
I'm not entirely convinced that virtual photons are a thing. The conventional thinking on photons is that a photon of energy is the amount of energy in a photon is Planck's constant times the frequency of the photon. So in a static field, what's the frequency? Basically, you have the frequency in the limit is going to 0. So how big is the photon in the limit where the frequency is going to 0? Well, it's 0. So if you look at it that way, I think what happens is that in static fields, the energy actually is truly a continuum, and you only get photons popping out as you're looking at dynamic fields, radiation moving from place to place. For instance, if you have two waves of different frequency, plane waves, interacting with each other, of course, each will be carrying photons of an energy that's equal to Planck's constant times the frequency of that plane wave. Now, if they have different frequencies involved, as they come together and interfere either constructively or destructively, what's going to happen is the individual photons are going to congeal into those concentrations of electrostatic or magnetostatic energy. And then as the waves pass through each other and separate, they will condense the appropriate sized photons to go with each wave. But in the process of doing it, they'll end up trading the energy that each started with. So the forward wave picks up energy from the reverse wave and vice versa. So that's how I believe that works.
That's interesting. Yeah, as I said, I only got partway through the book I was reading that was talking about virtual photons, but that's one of those things that, because the word virtual means it's not actually there, and then you're invoking this to say this is how the thing is actually working. And yeah, it's one of those where I just kind of stopped at that point, and I'm not sure what to do with something like that, because this I'm sure, I mean, underlying it sounds like it's simply a model. A model that is not in any sense intended to describe what's actually happening. Which can be fair.
Well, that's one of the big frustrations in physics is because we don't have a good model, you have a lot of people arguing about models. You have people who are saying, shut up and calculate. I think it was Sabine Hassenfelder who, like in the last year or so, she had this long conversation of, why are you using models? All these models of like the rubber sheet that is depressing, modeling the curvature of space for general relativity or other models of physics. That's not what's really happening. Stop using models. They'll just confuse you. And then the problem with that attitude, though, is you really can't help but think of physics and reality in terms of models. Your only choice is whether you look and are very deliberate and careful about what models you want to choose, or whether you just kind of take something for random. Like, for instance, the conventional model, to the extent people don't just say shut up and calculate. If you were thinking of a physical model for radiation, the conventional model that physicists would generally adhere to is, okay, I have this charge here, and when I wiggle that charge around, out pops a photon. And that's our model of electromagnetism and how it works. But there's this Zen, what's called a cone, a paradox that you're supposed to ponder in order to gain inner awareness. The concept of contemplating what is the sound of one hand clapping. And of course, that's nonsense because it takes two hands to clap. The concept of one hand clapping is nonsensical. You've reduced the problem beyond the point where the system can support the phenomenon that you're trying to describe. And just as the sound of one hand clapping makes absolutely no physical sense and is paradoxical, the radiation of one charge accelerating is similarly paradoxical. It takes at least two charges to accelerate. And if you can either do that in what's called a dipole, where you have equal and opposite charges that will oscillate against each other, or if you have a single charge, you have to have other charges, say, on the plates of a capacitor, setting up the field that is giving rise to that acceleration. But if you study the energy flow around that accelerating charge, an accelerating charge does not emit energy, it absorbs energy. If you think about it, that accelerating charge is like a little tiny current that's going, as the charge goes faster and faster, it's a current that's getting bigger and bigger and bigger. Well, there's more magnetic energy that's associated with that. It's absorbing energy and getting this bigger and bigger magnetic energy surrounding it. Or if you want to look at it mechanically, well, 1/2 mv squared is the kinetic energy. If it's going faster and faster, the kinetic energy is increasing. Whichever way you look at it, electrically or kinetically, an accelerating charge absorbs energy. It doesn't emit energy. So where is the radiation energy coming from? Well, if you look at the details of the energetics of a system like that, the radiation fields from that accelerating charge are propagating out, rippling through the much larger flow of fields and energy converging on the accelerating charge. And it's only at the edge of the capacitor where the fringing fields are starting to get really weak that the radiation field is big enough to be able to couple to some energy and grab onto it and radiate it away. So, the whole one charge accelerating model it doesn't make any sense. But because physicists, eschew models and want you to shut up and calculate, they don't seriously and critically analyze their models and try to figure out if maybe they could come up with a better model. They pick a poorly thought out model like the one charge accelerating model, and then when it doesn't work, well, throw their hands up. Models don't work. We shouldn't be using models. We should just be shutting up and calculating.
There's a really. Did you by any chance have you read any of the? And this is taking us very far afield, but there's a connection, I promise. Did you see any of any of the people who argued that one of the great malevolent forces on modern political discourse is Jon Stewart? Specifically, he made an appearance on, I think it was Crossfire, Crosstalk, something, a show like that, in which he gave a speech about how people with opposing viewpoints talking to each other civilly was destroying our civilization. And anyway, but he would always defend himself, like anytime anybody would criticize him. So he would give this great moral indignation about this or other things, and then whenever he himself would be attacked, he would just respond, "Oh, I'm just a comedian." And this is described as the clown nose on, clown nose off model of being a public figure. That whenever he wants to say anything, he takes the clown nose off, and he's full of moral indignation. And whenever anyone attacks him, he puts the clown nose on, and "Oh, I'm just a comedian." And do you see something analogous in that, using models when you want to persuade people, and then when the models become problematic, shut up and calculate?
Oh, I think that's a very interesting parallel you've identified, because that is kind of the mechanism that's going on. On the one hand, physicists use models all the time. That implicitly, really, a lot of it comes from Feynman diagrams. Now, if you ask a physicist and they think seriously about it, they realize Feynman diagrams, these diagrams of charges and photons interacting with each other, is really just a notational shorthand for keeping track of the terms in a series expansion when you're trying to do quantum electrodynamic calculations. So, if you press a physicist, they'll acknowledge, okay, yeah, it's just a shorthand for keeping track of the terms of the series expansion. But because that's what physicists are used to dealing with, they reify that model and they treat it as being real. And that's really the basis of the one charge accelerating model, or at least it popularized it a lot. There was an earlier model that's still taught to explain radiation called the kinked field line model. So if you have a point charge where the fields are radiating out in all directions, and then you move that charge, you'll get a little offset in the field line that then propagates out at the speed of light. So that kink in the field line that's rippling out from the charge, that's the radiation field. It's a horrible model because radiation has to be closed lines. And again, it's the same one charge radiating fallacy of radiation. A charge could never do that unless there were other charges and other fields giving rise to that acceleration. But yeah, when the model starts to have shortcomings, that's the point where the physicist will say, oh yeah, well, I was using that model, but of course, because you've now identified that my model doesn't work, well, that's because no models work and you should shut up and calculate. So, I mean, there really is, I like that, the clown nose on, clown nose off analogy, because that is very much what happens. It's models are great for explaining things so long as I want to explain something to you, but the moment you point out my model is wrong and you want to argue for your model, well, that's the point where I say, models are useless, just shut up and calculate.
Yeah, the very nature of persuasion is always narratively based, because human beings think in stories, because fundamentally narrative is the most fundamental thing there is. This is very easy for Christians and Jews, because God spoke the world into existence. And so it just becomes really, really easy, for us to see. But fundamentally, the world is narrative in a really technical sense. The world, everything we observe is time is change, and change is the structure of a narrative. It's things happening in a causal pattern. And so for us to understand the world, anything, we understand it by way of some kind of narrative, generally an abstracted narrative. And if you look at the structure of rhetoric is almost invariably sort of a series of micro narratives, where you'll put a few very, very small, sometimes 2 or 3 word narratives combined next to each other, where there's sort of like a plausible connection between these micro narratives, where you're spelling them out and then leaving the interstitial spaces for the imagination of the person you're talking to. And calculations are not narratives. Calculations are intrinsically static. You've got an equation, and it's this side is equal to that side. And so you can work this out, and you can reformulate it, and you can make manipulations to it, but you are intrinsically saying at all times that the one side is equal to the other side, and that you haven't changed anything. The whole reason you're allowed to do any mathematical calculations is because you have not changed anything. The moment you do something like multiply both, add 3 to only the right-hand side, well, you've broken the equation, you don't get to proceed. And so there's a fundamental static nature to calculations, and which is where they get their power from. But at the same time, that can't be persuasive because there's nothing narrative about it. And so if you want to persuade a human being, you have to give them some kind of narrative. And hence the model, that the bowling ball on the rubber sheet, that's a narrative. A bowling ball, rubber sheet, you know what happens. That's narrative, and therefore the mind can actually latch onto it. So it does make sense that you have to do this if you want to persuade anybody of anything, that you do. So, yes. So that's. But there is a problem when you're using something which you're intrinsically saying is wrong, or you're saying this model is wrong, but consider this model. There's the fundamental, reasonable question, rather, of, well, why would I consider a model that's wrong?
Well, absolutely. And one of the great influences on my approach actually to fiction and nonfiction, is this wonderful book by Jonathan Gottschall, which is called The Storytelling Animal. And what he does is marshal a lot of evidence from everything from neurochemistry to evolutionary psychology and so forth to argue that the correct definition of human beings is no, we're not flightless bipeds, or we're not tool makers. We're the storytelling animal, that stories are our tool of cognition, that we understand reality by looking at it and telling stories about it and about what's going on, and that we use those stories to interpret the facts of reality as we observe them. And he goes on to add that science is a story we tell about reality and about how reality works. And his sentiment there was echoed by Richard Feynman. Feynman once commented that if you wanted to try to condense the most amount of knowledge into the fewest amount of words, like if the world's going to be destroyed and you've got just a few seconds to scribble something on a sheet of paper to the generations to come that will capture and convey as much science as possible, he said what you should write is everything's made of atoms, because that's a very powerful concept. And once you understand that, a huge swath of chemistry starts to make sense. Things like why it's always the same ratio of hydrogen to oxygen to make up water, and just all kinds of things about how reality works, and Brownian motion and everything else. But what's interesting about that is that concept is very simple. I mean, you can tell a first grader everything's made of atoms. Atoms are little tiny things that are very difficult to break down further. They're the little kernels that make up everything. There's only 92 different kinds, excepting some radioactive ones and so forth. It's a very simple story. But at the same time, I mean, it gives you a narrative structure for understanding chemistry, but then you have to build upon that narrative structure with a lot more complexity before you could consider even calling yourself a chemist and claim that you really are a chemical scientist. And that's really the level that I'm trying to get at. The simple truth that I'm trying to convey is electromagnetism happens because fields guide energy. It's very simple. And I can explain that, fields look like waves, they propagate like waves, they radiate outward from their origin. I can talk about Huygens principle and how every spot on the wavefront becomes a source for further waves to propagate from there. And that explains the motion of waves and how waves reflect and refract and so forth. And then I have to talk about how they guide energy. And there are simple rules about how they guide energy. If you have a conducting surface, well, if it's not absorbing or radiating energy, the energy flow has to be parallel to the surface. And that explains, for instance, how a mirror or a perfect electric conductor works. The fields come down and bounce off of that surface. They come down and actually interact with the surface and bounce off. The energy in that interaction region where you have equal incident and reflected waves, the energy is moving parallel to the surface in that interaction region. So it's taking a different path through the system. And it was seeing example upon example like that. The example of if you have two beams intersecting each other, they trade energy. So the beams pass through each other, the energy bounces off each other. Example after example like that is what convinced me they're two different things, and the way to look at electromagnetism is that fields guide energy. And I think, like Feynman's everything's made of atoms, it's a very simple, easy to understand concept that's similarly very, very profound in its implications and applies across a wide swath of physical phenomena.
The thing about mirrors is fascinating and makes sense, because it's just one of those little niggles that I've always had is it really makes no sense that this is probably a high school physics, which is the wrong level of physics to use, but that the photon comes in, gets absorbed by the electron, jumps to a higher energy state, jumps back and re-emits, and somehow or other this is always at a fixed angle. And no, admittedly, I read a paper that was persuasive to me, which is saying extremely little given the level of my knowledge, that the Bohr model of the atom is simply wrong. And the way the person put it was that you shouldn't use the Bohr model of the atom because any intuition this gives you about an atom is wrong. And it gives so literally it doesn't do anything a model is supposed to do, because anything you might possibly intuit from it is not actually true about atoms. So it doesn't, and it's missing things that are true and gives you nothing that is true. So but all the same,
I mean, it gives you the complete spectrum of the hydrogen atom, and that's nothing to scoff at, and that's why people were so enamored with the model in the first place.
Interesting. Oh, okay. I maybe. I
mean, people will scoff at it because then, as you move beyond that, you start to have all of these other, line splitting and higher order effects, and we realize that it can't be little neat orbits like a little solar system. There's some more complicated diffuse wave action taking place there, but it's a perfectly good model for calculating the spectrum of the hydrogen atom, and
that is so fascinating.
A great starting point for understanding what's going on there.
That is very, very interesting. Very interesting. But just to finish off the previous thing, in the incredibly naive little solar system thing, the idea that the photon's going to hit and somehow manage to come back out again, always at the correct angle, in a mirror, makes precisely no sense. Now, obviously, there's so much about that that's wrong to begin with. But what you just described about the nature of the field interacting with the field in the plane, and thus the fields will naturally come off at a reflected angle, makes so much more intuitive sense than the whole absorption and re-emission. So much more sense. So anyway.
I can give you another example. If you have a transmission line, like for instance, you have two parallel wires that are guiding a wave down. Let's assume we just have a little impulse of energy. If it gets to the end of the line and we have an open or a short, it's going to be reflected. Now, if we have an open, it's going to bounce back with the electric field in the same orientation. So let's start with that case. So what you're going to have is this impulse where the leading edge hits the open at the end and starts to reflect back. And then it traverses half the length of the impulse as the trailing edge catches up with it. And at the moment that the reflected leading edge aligns with the trailing edge that hasn't hit the end of the line yet, at that moment, all of the energy is static and it's compressed into a space that's half the length of the original impulse. And then as the wave continues to propagate, it unwinds and the energy starts to flow again as the trailing edge passes through that wave. So the energy, most of the energy never makes it to the end of the line. It's just all of that energy gets compressed into half the length and then bounces and moves on off.
Interesting. Well, I can say I am very much looking forward to reading Volume 3 too.
Well, that's in Volume 3. The discussion of that and how that works.
Yeah. I'm looking forward to reading Volume 3 quite a bit. Anyway, so thank you for all the time that you've given me. It's been a fantastic conversation. I really appreciate it.
No, it's been a wonderful conversation. I've enjoyed talking with you about it, and I'm sure further questions will come up, and I'd be happy to come back another time and talk further.
Oh, that would be great. All right. Well, that's it for now. God bless. Well, if you made it this far, either you enjoyed it about as much as I did, or else you weren't in the room, I suppose. I'm going to assume it's the former, so links are in the description, and until next time, may you hit everything you aim at. If you like this video, then clicking the like button, according to YouTube, will make them more likely to recommend it to others. If you know anyone who might get something out of this video, then it would be kind to share it with them, or just share it on social media in general. And if you'd like to see future videos of mine, you can subscribe. And if you're not in the habit of checking your subscriptions page regularly, then I suggest clicking the notification bell and setting that to always, because otherwise subscribing to a channel basically just sort of like gives YouTube a hint that maybe it should consider recommending these videos to you, possibly at some point, if they think so. It's a funny world we live in. God bless.